Hi, this is a video about SOEN6441, Advanced Programming Practices. This is for week 12. In this video, I'm going to talk about Java generics. So Java generics is one of those topics that you learn, say, the last topics that you learn in a typical programming course about Java. For that reason, it tends to be somehow overlooked or going over it very quickly. One of the things that's important, as for any other programming language feature that you learn, is most important thing is to understand what it means and how it works, uh, under the hood in order to use it properly. Generics, especially Java generics, is one of those. So here, what I'm going to do is that, yes, I'm going to give some examples. I'm going to show, what's the syntax to use to express Java generics, but I'm also going to explain how it works in the hopes that students will better understand how to use it properly or what it actually means so that they can use it in an appropriate way. So what is generic programming? So in Java, you use Java generics. So that's language features that enables classes and methods that are implemented independently of some type that is used as an abstraction, as a type parameter of a class. So when you you define functions or member functions, you define parameters to these functions. Now, what that means is that you define some block of code, and you want to be able to reuse this block of code over and over by calling this function. Now, if you want to be able to use this block of code in as many possible situations as possible, you define parameters that enable you as a programmer, when you call this function, to define the context under which you're going to be calling this block of code. And then these parameters somehow parameterize the code and change somehow the behavior of this code according to what parameter values that you gave to this function when you called it. In this case, the parameters are values that you pass to the parameters of the function. In the notion of generic programming or Java generics, you have this notion of parameter, but it's the parameter of a class, and then the parameter or a method, and the parameter is a type. It's not a value, it's a type. So what you're doing is you're actually defining a class that inside of this class, there's going to be a parameter that is going to be a type. And then depending on what type you pass to this class as you create an object of this generic class, and this will have different behavior depending on what's the type parameter that is you have given to it when you instantiated an object of that kind or call this generic function. That's one of the misconceptions or concept that people don't necessarily properly understand. What is the notion of a type parameter? So essentially, what you want to be able to do is to use a certain generic class or generic member function in as many different contexts as possible. So, and you define your parameters as a type parameter of this class or this member function. Now, what this implies is that whatever code that you have in this class or these member functions that you make generic, the code should actually work for any of the types that you want to instantiate this class or this method with. Okay, so if you define a type parameter for a method, then the code that you have in the body of this method should work independently of what is the type that you use as a type parameter to this function. if you define some code here that does not work for some types, then you should actually put what is called a bound on this type parameter to make sure that you can only instantiate this piece of code or this method with the appropriate type for which you have code for inside of the body of this method. There are other languages that don't have type bounds, that still have generic programming embedded in the language, but Java provides this type bound notion. So then your generic types or your generic methods are in fact instantiated to form a parameterized type. So once you instantiate, create a variable that, for example, so you have a generic class. If you create a variable of this kind, for example, if you have a stack, which is a stack of any type T, it's essentially a stack that can contain values of any kind that you define a class for. Then once you have a stack of string, then the type, the class, the type stack of string is actually a parameterized type. So yes, it's a type that you can use, but it is it's a parameterized type because you used a parameter to actually define it, to declare this variable. So having a stack class, a generic stack class, enables you to create different parameterized types, such as, for example, a stack of string or a stack of integer. Okay, so that's it for this introduction. Now, a little bit of history. I like to give a little bit of a history in the beginning of my topics. Here it goes. So again, this notion of generic classes, yes, it became, I would say, popular not so early in the history of programming languages. This idea is kind of old, as many ideas in computer science, but you know, as to whether it became popular, when it became popular, it's rather in the probably the 1990s. So there was the original idea is from McElroy in 1968, where he was imagining essentially that you could define a piece of software in abstract terms, and then depending on where you want to use this piece of software, then you would generate a piece of software that would adapt to the specific situation in which you want to use it. Okay. So essentially, it's producing software according to the context in which it would eventually be used. That's the if you trace back the history of this notion of generic programming, this is where it all comes from. Now, it's very remote from what we know nowadays as, for example, generic Java generics, but this is the original idea, you might say. Then it became more concrete as implemented in a language called CLU by mainly Barbara Liskov in the 1970s. And then eventually there was evolutions of this. And then eventually what you came to have as Java generics actually was implemented in the late 1990s. That was actually after things like C++ templates. Java generics look like C++ templates. C++ templates were there before Java generics. As for many things in Java, the syntax of Java generics was somehow adopted from C++. Though very important to understand, as I will point out later, that Java generics and C++ templates, even though they look the same, syntactically the same, syntactically speaking, they are not the same thing. They don't work in the same way. Okay. So how does this work? Implementation of Java generics. So here I'm going to explain how it works as you actually generating writing your Java generic class. How does it make it so that it becomes an executable class? What's the procedure involved? Now, there's different ways that generic programming or template metaprogramming does it. In Java, it's using a technique which is called type erasure. So it's essentially translating at compile time, it's translating your Java generic class or method into what is called a raw type. So a raw type is essentially the bytecode implementation of your generic class. But we'll give an example of that later on in the following slides. So what it does is that it actually eliminates all generic type information at compile time. So all these things that you have in the angle brackets actually disappears at compile time, then becomes somehow a regular class, okay, which is as a class is transformed from a generic class to a normal class through type erasure. This class is named a raw type. We'll see some examples of that later. And then eventually, if you have bounds on your type parameters, then they are actually respected also by the type erasure implemented at compile time. Then eventually what this type erasure does is that it ensures that the code, whatever you use this generic class in your code, that it's going to be type correct. So that's one of the main things that Java generics enables, is to have generic code that can be successfully type checked at compile time and at runtime. So here's a little blurb about the Java generics versus C++ templates. So again, repeat, they look the same. If you know C++ templates, they look the same. You might think it is the same. It is not the same. So some of the goals are the same, but even there are some things that you can do with C++ templates that you cannot do with Java generics. Or things like in C++ templates, you don't have type bounds. In Java generics, you do have type bounds. There are differences. Arguably, C++ templates are more powerful than Java generics. So they look syntactically the same, but they're not the same. In Java generics, what it uses is type erasure at compile time to essentially transform your generic class in a single class, normal class that's going to be used at runtime in a generic way. Whereas if you do template metaprogramming with C++, what is happening is that for every usage that you make of your template, the template, there's a template processor that basically reads your templates, and depending on how you use this template, so you have a string, a stack template, you want to have a stack of strings, then the template processor is going to read your template stack class, and then it's going to generate a specific class that is a stack of strings. And it does that for every possible use that you make of a template. And then this class is these classes that are generated, template instances, are each specific and separate different classes. That's not what is actually happening in Java. If you have in Java a stack generic class, it's going to be converted into a single raw stack class. So could talk about this for a long time, but just to say that it's not the same, and just to explain a little bit of what is the difference. Now for the type erasure, let's start with this, go ahead with this example here leading to the type explanation of the type erasure. So how do you define or declare a generic class or generic methods? So you have to you essentially declare a seemingly normal class, except that you have this angled brackets notation after the name of the class here, in which inside of these angled brackets, you would put a parameter. Now this parameter is a type parameter. Now here, the name of this parameter is t. You will see all over the place and all people's code and textbooks, you will see always the variable t that is being used. It doesn't mean that it has to be t, it's just that is some kind of convention that people used and are still using. So here you're declaring this variable t, which is the type parameter of this class box, which makes it a generic class in Java. Now what that means is, as you see here, I'm using t as the type parameter. So then what that allows me is to use t wherever I have in the scope of this class here, of the definition of this class. Then I can use t any place I would be able to use a type. For example, here I'm declaring this private member of this box as named t, little t, but is of type t. So that would, for example, enable me to create later on a box of integers. Then what's going to happen is that there's going to be inside of this box a variable named little t, which is an integer. So when I instantiate this type, it's going to create a parameterized type that is using, in this case, integer as a type. Okay. So essentially what happens is that whenever there's t in my code here, it's going to be somehow replaced by integer. Okay. So I will have an integer t, then my set method will take an integer and my get method will return an integer. And then wherever else I'm using t in my code, it would actually replace it by the value of this parameter type. So for classes, the type is included in the angular brackets after the name of the class. For methods, however, you can create, so that's a parameter, that's a generic class. You can have a generic method of a class, in which case you actually put the type between the angled brackets before the return type of the actual function that is using this parameter type. Now this function, for example, it uses this parameter type, this type parameter as, for example, it's the type of its parameter. Okay. So here the parameter of this function is of type u, which is the parameter type of this function, which allows somebody to call inspect with additional type method with any type. Because as we will see later, you may have bounds. In this case, there is no bound to this type parameter. Here, there is a bound for t, which says it's bound to the type number. Explain that later. The methods also here, this is another thing that some people don't really understand, is that even if you declare a class box that has a type parameter, which makes it a generic class, you can have a method inside of a generic class that uses their own type, their own local type parameter. So a method inside of a generic class can define its own type parameter that is different from the type parameter of its the class that contains it. Okay, so and then how is this type instantiation done? If you want to create a box, then what you need to do is to specify in the variable declaration for a variable of this kind, you have to use the angle brackets to actually instantiate this box with the type integer. So here you essentially have a box of integer. And then you can use it to put integers in the box, because now t is now integer. How do you make the instantiation when you want to call a parametered member function? You basically call the member function, and then in this case, the instantiation is made through the passing of this parameter here, which is clearly a string. So that makes actually u being a string type. That's why if you would type here using a printout on the console, if you would type the name of this class, then it would actually type the string name. And then also, as you call, for example, if you call the get function of your integer box, which is a box of integer, and you see the get, the type of the return type of the get function is t. So then the return type, because integer is here, you've provided integer as the type parameter, then the return type of the get is integer. So that's why it allows you to put the result of the get function into a variable of type integer. That's why I was saying that because of this mechanism, this allows the compiler and the runtime system to make type checks and verify that your program is type correct at compile time, for example, as well as at runtime. Now, how does this work? How does this happen? Idea is that, this at runtime, you would be able to look at your bytecode, and this idea here of the type parameter does not exist. Okay, so yeah, somehow the compiler has to remove this concept so that at execution time, it becomes a regular class, okay, as any other class. So that's what is known as a type erasure. So what's happening is that as this class here is being compiled, then it's going to essentially replace t, all instances of t, by the upper bound of what t is. So if you don't have if you do have a bound to your variable t, then it's going to replace all occurrences of t by number. If there is no bound, then the upper bound would be the class object. So it would replace all instances of t, occurrences of t into replaced by object. That's what would happen with this one here, as it does not have any bound. So you see, this is the actual raw type that would be generated by the type erasure at compile time. So this becomes a regular class box, and then all occurrences of t are replaced by number. So that allows you to, in the box, you can put only things which are number. So you could not put, you cannot create a box of string for that reason, because all that you can manipulate is numbers, and that string is of course not a subclass of number. And then you see that for the parameterized member function here, as it does not have any bound, then it replaces the u by object. Then eventually also, as you are, it needs also to do the type erasure for when you're actually using this class definition and this method definition. So for example, here you're using the box here to declare this variable. So it needs to remove this notion here of type parameter. So it's essentially allowing at runtime to create a box, not a box of integer, it just creates a box which has been type erased. Then when you actually calling these member functions, which are parameterized, then it needs actually to translate the to do a type transformation typecast into the type that is actually being used at runtime. So here the get function is returning a number, but here you want to put this number into an integer variable. So you need to downcast this number into an integer. And it knows how to transform this this number in an integer. Why? Because what you did is to create a box of integer. So it knows that this get here needs to be typecast into this specific integer here from number. So that's a process that is happening when you compile your code and eventually as you execute your code. So it is this generic class here does not exist. These type parameters don't exist at runtime. They are removed by the compiler. Now, let's backtrack a bit and try to figure out why do we need that? So I might say, for example, I'm going to create my let's say I want to create a linked list that can contain any kind of value. Now, what's the meaning of any kind of value in Java? You might say, well, this is a linked list of objects, of values that are of the ultimate super type, which is the object type. So eventually I can actually, if I'm creating such a class where my linked list is inherently a linked list of objects, then I can actually put a string in as a member of the linked list, and or a date as a member of the linked list, because string and date are both subclasses of objects. So I can put these things into my linked list of objects. However, when I want to actually use these values, for example, I can go list.getZero, and then I want to extract this string and then use it. Now, the thing is that when I call getZero here, what its return type is object. So I'm not be able to actually put this object into a string. So I would need to downcast the object that is returned by get into a string, and then I'm getting able to use it as a string. And the same thing with my second thing that I put in my linked list here. If I want to use it as a date, then I have to get it. It's now an object. Now I need to downcast it as a date. And every time I would want to do that, then I need to know what is the type of this actual element so that I can downcast it. Now here, that's fine because I know what, in my code, it's clear what were each of the types of each of these two things that I put there. But sometimes, you cannot predict. Okay, so it would be, not so flexible to use. Okay, so that's this flexibility and this adaptability that is, and as well as ensuring that the proper type checking is made at both at compile time and at runtime, that makes Java generics a real adaptable solution. Okay. So here, this is what we want to achieve. So here you have this linked list generic type that you can instantiate using, for example, a string. So you will have a linked list of string, and then you can put strings into your linked list of strings. Of course, then you're not able to put things that are not a string into this particular instance of your linked list. Then eventually you're able to get your elements and they're automatically typecast into a string. And then you can do the same for linked list of integer. Okay. So what is the goal then of this type erasure mechanism and the generic classes is to allow the programmer to define classes that are valid in different contexts of use, and to ensure that they are correctly checked in every specific context of use. That's the real goal of generic programming, that you can write a piece of code, a class that can be used for different types when it's necessary, and that the compiler can actually check for every possible usage of this generic class that it is actually properly used. Now let's go into more detail about the type bounds. So when you define a generic class or method, you can be defining a type bound for the parameter. So the type bound, first of all, can be only a reference type. So it cannot be a basic type. So for example, it cannot be an integer or float or things like this. That is not a type. Okay. That is not a class. So it doesn't work for basic types. And then it restricts the set of types that can be used as type parameters and give access to the non-static methods of this type. So the type parameter can be unbounded. Remember, in my method, my method in the example, it used an unbounded type parameter. And you can have, in the case of our box, then it was a bounded type. It was bound to numbers. You can actually have more than one bound. You can have a bound to one type, and you can have a bound to as many interfaces as you want, as we will see later. Now, why would you want to have bounds? Reason is, as I mentioned in the beginning of this lecture, is as you write code inside, for example, of this class, it's possible that, yes, you want this class to be, to operate with as many different types as possible. But when you implement the code for how this class is actually working, you need to write code to do the implementation. Now, very often, of course, when you write code, you would call different operators or different functions to manipulate the data that this object is containing. So you would end up using very type-specific operators or methods. Now, of course, if you want your generic class to be applicable to as many classes as possible, you're going to use as your operators and your the member functions that you're using to manipulate this data so that they are as generic as possible. But there's a limit to that. Yeah. So if there is a limit to the operations that you're doing, for example, you might be doing some operations that only involve numbers, manipulating numbers, then you have to, if your code has using operators that is manipulating numbers, then you have to bind this class to the type number so that your code will actually work for all the family of classes of numbers. So that's why you have bounds on classes. Here, I designed an example about, took an example from, which is actually a typical example you see in textbooks, is a pair. A pair, what is a pair? A pair is essentially a class that contains, like my box was, for example, a box of integer that contains only one element, which is, for example, an integer. A pair actually is the same thing. It's a box that contains two elements, which in this case can be of two different types. Okay, so it's like a box that contains two elements of different types. That's what is the notion of the pair. Very simple kind of thing. But as the example, my example here wants to show that even though this is a very simple example, it can quickly degenerate into something that is not so simple if you want to put more restrictions on what this class can do or should do. So here, this is about type bounds. So what's the syntax of the type of specifying type bounds is you have inside of the angle brackets, you have the type parameter, which is your name, which was T in our example. Then you use the extends keyword. That's one of the things that's confusing. It seems to say that this type here inherits from this other class here. That's not the case. That's a confusing term to use, yes, but that's the term that is used. What that means is that whatever is the type parameter here that you provide, it must be a subclass of this class that you have here. Okay. So it's a restriction that you give to this. You're not declaring that this is a subtype of this. You are restraining this to be a subclass of this. It's a related concept, but it's not the same concept. And then, as in Java, you cannot have multiple inheritance, but we want to be able to have bound restrictions on possibly on many different types. We don't have multiple inheritance, though we have interfaces in Java. So you can, if you want to bind a certain type parameter to a class as well as to some other interfaces, then you put ampersand here as a, you basically have an ampersand separated list of interface names, possibly optionally after the class here. So essentially you have an ampersand separated list where at most one of these can be a class name and all the others would be interface names. Now, as we will see later, so you can actually have, in this case, the pair has actually two parameters because it contains two elements which are possibly of different types. So you see that my pair here actually has two parameters, one named A and one named B. And then here I have a bound on each of my two parameters. So essentially A must be implementing the interface comparable A. What that means is that what I want is that my first element of my pair, I want it to be comparable to all the other elements of a pair which are of the same type. And also I want this to be implementing whatever is my type parameter here, should be also implementing clonable because I'm going to use the clone interface to make copies of my objects. Then the same should apply to my second parameter. It should extend, it should implement a clonable B interface as well as a clonable interface. Now you see here that it says A extends and then the name of an interface. So it seems to be wrong because normally when you have extends, it should be a type name here, a class name here. Now keep in mind that extends here, as I said here, extends basically is there to express that you have a type restriction on this name here, and that is the list of all the type restrictions. Then also I want to specify that this class actually itself, this class pair, implements a comparable interface. In this case, it is implementing the comparable pair AB class, so that I have two pairs, I can actually compare them together. So the class pair implements comparable, the class pair AB implements comparable pair AB, as well as clonable. Okay. Now, all this here, because I wanted to make my pair class to be able to compare elements of or variables of a pair class with one another. I needed to have it comparable, and then for each of the elements of the pair to be themselves comparable with the other elements of another pair. Okay. You see that I'm just adding something a little bit more handy. And then it lead to have this very complex, well, reasonably complex specification for my generic class. Now let's look at some examples. So here I have my pair class, so which is my pair of x, y. In this case, I'm keeping it simple, and then I did not put these restrictions. Okay. In this case, I only have a pair of x, y, and I don't put any restriction on what should be x and y, because in this case, I don't want them to be comparable. I will explain how to make them comparable later. So let's assume I have this class, this generic class pair that can contain element A and B of type X and Y. And here I have this other class that's actually using element of type pair in the form of the parameter of this static method that actually implements. So this add method, what it wants to do is to transform the value of get first and the value of get second into a double number and then add them. Okay. Now, in this case, of course, if I have x and y, which is not a subclass of number, then I cannot actually call double value. For example, if I pass to this function here, I pass a pair of string, then get first will return a string. I cannot actually call dot double value on the string. It just doesn't work. The type checking doesn't work. So that's why when I actually declare this member function here, I have to put a bound declaration on the types of these two parameters, saying that if I'm calling add function that receives a pair, then the types of A and B must be a subtype of number. Because if it's not, then this double value here would not work. So you see, that's the real reason why you want to have type bounds on the definition of your generic code. Generally, this is because there is some code inside of the implementation that is restricted to a very specific type or family of types. So here you're essentially somehow restraining the instantiation of this parameter here with only type number or subtype of number, so that this double value function will actually work when you call this member function. Now here's a slightly more complex example. Here you have swap. Of course, the notion of a swap function is that you would interchange the two values that it receives. In this case, what it wants to do is to switch the A and the B in a pair. Now here, the swap function, it wants to switch essentially the A and the B, which is the type of A is A and the type of B is B. So essentially what's going to happen is that you're going to switch these two. So if it was a pair of int string, where x is int and y is string, then it's going to be, when you swap it, it's going to be a pair of string int. Okay. So if you swap a pair of AB, what is the type? The returning type is a pair of BA. Then here, it doesn't matter what is here. I don't have type bounds. Why? Because the only thing I'm doing is I'm calling get of each of the two, and then put them, basically swap the two values and then return the swapped, the pair that has the swapped values. I'm not applying any operations on the content. Just getting the first and second, making the swap, and then returning the actual swapped pair. Okay. That's why I'm not doing type specific operations here. That's why I don't need to have a type bound. Okay. So again, type bounds are there only for cases where in the code you are making type-specific operations on the parameterized values. Now, this heavily relates to wildcards. It's similar concept, but that is, because it is similar, it also is confusing to a lot of people. So what is a wildcard? A wildcard is a syntactic construct that is used to denote a family of types in a generic class or method instantiation. Here, what you were doing, you were actually defining type bounds, which are essentially limits to what type you can actually use. But here it is at the level of the definition of a function. Okay. Here, what you are doing is that you are putting somehow bounds on, you're defining a type variable, but this is a type variable that is used at instantiation. Okay. It's not at the level of the definition of a class or the definition of a method. It's rather at the definition of a variable, okay, that you're going to instantiate with a generic object. So the type bounds are happening at definition, whereas the wildcards are happening at instantiation. It's kind of the same concept, except that it's not applying at the same level, at the same place in your code. Now, wildcards can also have bounds. Okay, that's of course what makes it confusing as to what's the relationship between these two concepts, because they can also have bounds. So the generic, the most general concept of a wildcard is using the question mark. Okay? It's like you're expressing that something is of a type that is unknown. You can put bounds on this unknown by using the extends keyword. So for example, if you go question mark extends B, then you are saying that whatever question mark is, it must be B or one of subtypes of B. But if you're using super after the question mark, then you say you go question mark super G, then what this means is that whatever question mark is, the only valid cases would be G or a super type of G. Now, what do you use that for? You might say, for example, I want to declare an array list named a list, and then I want to be able to use at one point as an array list of string, and at another point I want to use it as an array list of integer. Okay. Maybe you want to do that. Now, in this case, you would have to declare your a list as an array list of question mark, so that eventually when you instantiate it, the runtime system is going to be able to realize that a list is now an array list of string, and that it's valid to actually declare it as an array list of you don't know what yet. Okay. So that's what is a wildcard. See, I'm declaring a variable. I want to instantiate a variable, which is of a type of a generic type, but I don't want at this point to specify what exact type parameter I'm going to use for the instantiation of this variable. I'm going to delay that to runtime. Okay. So that's not a very interesting case. What is the most interesting case is, of course, when you declare a function parameter, a member function parameter. For example, you may want to declare a member function called print collection that receives a collection, and what it does is basically iterates over the collection and then prints out the values on the console. But this way, this print collection is declared as a collection of anything. Then whatever is a collection of string or collection of int or collection of whatever else, the code would still work. So this print collection can now work to actually print a collection of any kind of value. That's the power of the wildcards. So you see that this is not the same as your type parameter. The type parameter, like the T that we used to have, is at the level of the class declaration. Here, this question mark here is different, in terms of meaning, because here you're declaring a variable of a certain type, and you don't want to specify what is the exact type parameter that you want to use. You want to keep it flexible so that it can at runtime be used for various types. Other interesting that may happen, let's say you have a function that wants to copy two lists, copy one list into another. And then you want to make it so that it's possible, yes, to copy a list of strings into a list of strings, but you also want to be able to copy, for example, a list, I don't know, a list of integers into a list of numbers, where integer is a subclass of number. So the way to express this here is using the extends and super. So here you would say you want to be able to copy a list of any subtype of T into a list of a supertype of T. That would allow to copy, of course, T can be exactly the same type, because that's what is the definition of extends and super. So if you have question mark super G, G is included. If you would have question mark extends G, then that would include G also. So this works, for example, copying a list of strings into a list of strings, but it also works if you want to copy a list of integers, which is a subtype of number, into a list of numbers. But you should not be able to do the inverse. So that's why you have these type bounds here that are, yes, allowing to copy into a list into another, but respecting the fact that sometimes you want to put a list of a subkind in the list of the superkind. So that's for that kind of thing that this extends and super applied to the wildcard is handy. Now, let's look a little bit further into some of the potential problems that are related to many of the things I've said yet. Here, I'm creating this class, this generic class named basket. So it's a basket of E. And eventually, I have a class fruit, and then a class apple that extends fruit, and orange that extends fruit. So here I have this very simple class inheritance, and then I have a basket that eventually I'm going to put fruit or apples or oranges in my basket. Here, one of the things I want to show is that there's no relationship between basket and the inheritance relationships between apple and orange and fruit. Okay. You can have a basket of oranges. It doesn't mean that it becomes a basket of fruit. There's no relationship between the basket itself and the type of element that is put in the basket. Okay, so I can actually, this is my generic type basket. You remember when we define, when I explained to you what is the raw type? So eventually at runtime, you would use a basket, the class basket, that is the resulting class from the type erasure, which is the raw type. You are in fact actually allowed to use a raw type in your code. So you can create a new basket, which you instantiate, and then you put this object into a container that is of type basket. You're allowed to do that, but the compiler would warn you that this is potentially problematic. Why is it problematic? Because here you're using the container itself. So you could, yes, you could use this basket B, but the point is that it would not, all the fancy type conversion that would be happening as I was explaining here, this type conversion would actually not be happening if you're using directly the raw type in your code. So yes, you can use it, but it's much less flexible than if you're using the parameterized type here. Okay. So that's why what you want to do is really the proper way to do it is to use this here. So yes, you're able to create a new basket of fruit and instantiate it with the raw type basket. But again, that would not works very well if you are, for example, extracting the fruit from the basket of fruit and then expecting that, for example, it's going to be an orange that's going to come out. It's going to actually be an object that is going to come out from your raw type. But if you do it this way here, then everything is going to be fine. So yes, you can use the raw types explicitly, but it's not that useful. It may seem like it's a solution. Sometimes it is, but you have to be careful. Okay, here I'm saying I want to create my basket of apple, and then I want to instantiate it with a basket of fruit. Now, some people might say, well, this is fruit, and I want to put it into an apple. It's like there's a kind of a downcast that's happening, so that's not possible. Okay. A downcast that would need to happen. That's not possible. Well, yes, this is not possible, but that's not the reason why it's not possible. Because here you're creating a basket of apple, and fruit is not the same type. So that's why it's not possible. It's not because apple and of the relationship between apple and fruit that is not used properly. It's because it's not the same type, period. Okay. The basket does not become the type of object that it contains. Okay. There's no relationship between a basket of apple being a superclass of a basket of fruit. There's no such thing. It's just two separate classes as far as the type checker is concerned. So that's why, even if you would say, I'm creating a basket of fruit and instantiate it with a basket of apple, you might think, well, fruit is a subclass of apple, that should work. No, it still doesn't work because basket of fruit is a class, basket of apple is another class. They are unrelated, so you cannot make this assignment. If you want to do something like this, then what you should do is to create yourself a basket of apple and then put it into a basket of question mark. Okay. Then that would allow you to use B5. In this case, after this declaration here, after this assignment, you'll be able to use B5 as a basket of apples. However, you cannot instantiate or call the constructor of a basket of question mark. Of course, because the runtime system would not know what kind of basket to create. Okay. Here's basically a container that is declared, and then it's instantiated with that. Here you're instantiating an object of an unknown type, okay, which of course is not possible. So you see there's a lot of things here that are happening, a lot of concepts and so on, and these are kind of meta concepts, so that's why it's not that easy to grasp compared to normal Java, you might say. Now, let's come back to our, let's wrap it up with our complete example here. Here I have an immutable generic pair class. Why immutable? Because as I set my first and second data member, they are declared as final, so I can create them, but I cannot change them after. The only thing I can do is to get them because they are final. That's why it's an immutable class. Nothing to do with generic, I just made an immutable class. It is a generic class because I have these two type parameters here, which are type of first and type of second. In my previous example, I was using A or B or T and so on. Here I'm just using different names. So these are my two type parameters of my class, my generic class pair. And you see that if I have a type of first and type of second, that allows me to use these two names in place where I'm going to be using other types in my implementation. So if I have later on, I instantiate a pair of string int, then this is going to, the first is going to now be a string, and then the second is going to be, the type is going to be string, so on and so forth. Then of course my constructor needs to use these two types here, which are of course respectively the same type of first and second. Here I actually have a copy constructor. So I'm actually taking a pair of type first, type second, and then I'm creating a new object pair out of this pair that was passed as a parameter. So the copy constructor, and the type of its parameter is exactly the same type as the type specified here, as it should. Then when I call get first and get second, it returns type an object of type of first, and respectively an object of type of second. Then and then the very simple implementation that it has is to print to the console the values as well as the class name of each of the respective members. Okay. So you see here that my code, it does not use type-specific data manipulation involved in first and second. The only thing I do to manipulate these values is to return it, which is not type-specific, and to actually print their type, which is not type specific, and to actually call their toString data member function, which is not type specific either, because all classes have a toString method. Okay. So none of the code I have here is actually type specific. That's why I don't have bounds on my types here. If I would start doing some manipulation on first and second, which would be type specific, then I would need to have bounds on these type variables. But in this case, I don't. So here's what I can do with this pair class. So here I'm having a pair of string integer, and then I'm instantiated with a pair that is going to contain hello and then 1. Then if I go and print out this thing here, then it's going to be printing the type of the first, first, which is string, and then the value, which is hello, and then the type of this, the second, which is integer, and its value, which is now 1. Then I can create a series of such objects by having, for example, here I'm creating an array list of integer and an array list of strings that contain respectively 1, 2, 3, the value 1, 2, 3, and then the strings 1, 2, 3, which is French for 1, 2, 3. Then here I'm creating this for loop here that essentially takes the first of this and pairs it with the first of this, second of this paired with second of this, and the third one with the paired with the third one here. That's what this does here. Then I'm printing them out. So essentially I'm putting 1, 1, 2, 2, 2, and 3, 3, respectively all integers and strings, right? So that's what I can use this class for. Now, what if I want, as I hinted at before, I want to make these pairs comparable, so that, for example, I can compare my two, here I have two objects of type integer string. What if I want to compare these two to figure out which one is for example, you want to compare two numbers. If you compare two numbers, and you can use the compare to method to compare two numbers. If one is bigger than the other, then the compare to method is going to return positive value. If they're equal, it's going to return 0. And if it's lesser, it's going to return a negative value. Okay, that's what I want to use. I want to be able to use compare to between two objects of type pair. For example, I want to compare this one with this one here and figure out which one comes first, essentially as far as the compare to operator is concerned. Now, the compare to method point is that it's an interface that is called comparable. Okay. So here I'm creating another class called comparable pair. So it's going to be the same class I had before. It has first and second. It has a constructor. It has a copy constructor. It has a toString. It has a get first, get second. But then what I want to do is to enable compare to interface on this comparable pair class. So it will essentially implement the comparable interface. So it's my comparable pair has, as my pair has two type parameters, type of first and type of second. And thus it must implement comparable pair type of first, type of second, because you want to be able to compare two elements of this type, the type being comparable pair type of first, type of second. Then what I do is as this class implements comparable, that forces it to implement the method compare to. So here I have my method compare to. And then what it does is it compares this current object with another object that is passed as a parameter. So the type of this parameter is comparable pair, type of first, type of second, just like the original pair itself. Then what I do here is I actually use compare to between the two first element of the two pairs and compare to of the second element of the two pairs. So what I'm doing here is I'm forcing the type of first and the type of second to be implementing the comparable interface. Okay. If this code is to work, then first and second must implement the comparable interface because I'm using the compare to method. So if I want this code to work, first and second must be comparable between each other. Or the first of one object should be comparable to the first of another object, and the second of one object should be comparable to the second of the other object that I want to compare. So that's why I have that type of first should implement the comparable interface, and then type of second should implement the comparable interface. So type of first extends comparable type of first, and type of second extends comparable type of second. So this is how I came to have this very long specification for my class. I'm just here expressing something very simple, which is a pair. And just by adding this simple yet very useful notion of two pairs being comparable, then it forces me to have all this specification here. All this because I wanted to have compare to, and then in the implementation of compare to, I actually use compare to on each of the first and second. So you see that even though I'm going to have a class that is extremely flexible. Its type checking is going to be well done at compile time as well as in runtime. Yes, this class is very reusable, but it's, conceptually, it's to achieve this reusability and the type checking and so on, it forces you to have more complexity in order for the type checking to happen by the compiler. Then eventually that allows me to create comparable pairs such as I had before, and then it enables me to actually compare them by using the compare to operator. Okay, so here eventually what I'm doing is I'm comparing the first one with the second one with the third one with the fourth one, and then the fourth one with the fifth one. And then eventually what it does is that it compares 3 and 4 and the string 3 and 4. And then it actually is returning the compared values between the two. Well, let's go into the definition, how I implemented the compare to. So I actually, compare to is a method or a function that returns an integer. If the first thing that you want to compare, the object you want to compare is lower than the object that you pass as a parameter to compare to, then it is, if they are equal, then it's, if they are the same, then it's 0. If the first one is lower than the other, then it's going to be a negative number. If the second one, the first one is higher than the parameter, then it's going to be a positive number. Okay. What I do is that I check if compare of the result of comparing the first is not equal to 0, then you return compare first. And if not, then you return compare second. Now, for example, if it's numbers, then as the first one is, the second one is higher, then it returns the parameter. Here, this is the object here, is the parameter that you pass. It's this one here. And then the P here is this one here in the first call here. So it checks if 4 is greater than 3. Yes. So it returns a positive integer, which is in this case 1. In the second case, I'm comparing 1 with 4, which is lower, so it returns a negative number. In the third case, I'm comparing 1 and 1. So that's the case where they are actually not equal. So then I would actually return compare of the two here. So compare to of two strings is the lexical distance between the two strings. That's actually in this case -6. And then if I actually compare two pairs which are the same, so the last two ones are the same. So if they are the same, then by way of my logic, it actually returns the correct thing, which is to say that they are the same, which is to return 0 as far as compare to is concerned. So you see here, this was very simple class, but things are getting complex. Well, you know, utility has very often complexity cost. So yes, here you have a very powerful kind of class that you can reuse all over the place in lots of different contexts. But to express it, you know, the more you want to add some features, the more you need to invest some time in making it work correctly. The more you add some code that does interesting things, the more you are restricting the types that it applies to, and the more your specification for your type parameters and the bounds and so on become more complex. Okay. So that's it for this lecture. Thank you.